Hey, thanks a lot. My name is Doug Down. I'm from McMaster University in Hamilton, Canada. So this is joint work with an undergraduate student that I've been working with, Jingze. So I'm going to talk about combining two server control policies for energy efficiency in basically stylized data center model. We'll see it's very, very stylized in a minute, but these are two server control policies. If you remember back from the afternoon keynote, when we're talking about the flexibility within a data center, I'm going to talk about two of the mechanisms that were brought up there. So the two of these are, the first one is that if I have a server, typically I have something called dynamic frequency scaling available. So the idea behind this is that if I look at a server, a linear increase in the speed of the CPU yields quadratic or higher increase in power consumption. So essentially, if I think about the other way around, just think in the back of your mind, if I half the speed of my server, then I say I get a decrease by a factor of 4 in the power consumption of the server. So I can slow things down at sort of more than linear decrease in power consumption. Now, as been pointed out in a number of talks, this still doesn't deal with the issue that data centers spend a significant amount of their time idle. And even with today's technology, idle servers still consume a significant amount of power. Typically these days, we're talking maybe 30% of the busy power. So it's getting better and better, but this is still a significant concern. So what people have proposed is, okay, what we can do on top of that is on-off control of servers. So what I can do is I can just turn the servers off when they're not needed. And of course, the issue with that is that these lead to increased response times, so decreased performance of my system due to the need to actually turn servers on. So if I'm using, say, auto scaling or these kind of things where I'm turning servers on, there's still some time to actually boot up a server. Now, one thing I want to comment on here, I think that's maybe worthwhile for this community, is that most of the work that people in looking at analytic models, one thing they don't consider with these mechanisms, dynamic frequency scaling and on-off control of servers, is the impact they have on server lifetime. So if you're looking at total life cycle of a server, it's not clear that these things might have an impact on server lifetimes. If I talk to my mechanical engineering colleagues, they say that these two things are going to create thermal stress on your servers. Those thermal stresses are the thing that determines server lifetime. So there's been a bunch of work, for example, on, you might have seen work on proposals to run data centers hotter in order to reduce power consumption. There's been work on looking at server lifetimes for, turning up the heat in this, but these, it's a little more murky. So there's an extensive literature for how to employ each of these mechanisms, both in terms of more abstract mathematical models, and I'm going to give you a simple one of these in a minute, queuing theoretic model, and from the system side. But there's not a lot of work about how these two mechanisms interact with each other, so that I have the ability both to adjust the frequency of my servers and to turn them on and off. And so what we were interested in here is looking at how to use these two things together. So here, I'm just going to give you a really, really simple model that we use. It's just a single server, so this is kind of a starting point. It's a single server, and we built a queuing theoretic model. So we have arrivals. So if you're not familiar with some of these things, that's fine. But we have an arrival process that has a fixed rate lambda that we assume that we know. And basically, I'm going to give you the option to run this server at two different processing rates. Rate mu slow and rate mu fast. I get those two choices. The warming times, this is the time to turn on a server, is exponentially distributed, which is a bad assumption in practice, but we'll assume it for now, with rate gamma. So this means that the mean time to turn on a server is 1 over gamma. And then there's different power consumptions depending on the state of the server. There's PI when it's idle, PW when it's turning on, PS when I'm operating at the slow rate, and PF when it's operating the fast rate. And I won't go into this, but this assumption just assumes that there's a trade-off between the power consumption and the speed of the two particular rates. So what I want to minimize is this. So I have a cost function that's the mean response time, so the performance of my system, plus some weight times the mean power consumption. So I'm just trading off those two things with a simple cost function. So what do I do here? Basically, I'm optimizing over these things. I have some threshold. I'm looking at the number of jobs waiting at the server, a threshold for moving to the faster speed, a 0-1 variable that just decides when this server becomes idle, do I turn it off or not? And then a threshold for turning the server on if I choose to actually turn the server off. So the details will be in this full paper, but what we can do with this very, very simple model is we can get explicit expressions for those two quantities. We model the system as a continuous time Markov chain. If you're familiar with this, we can analyze this, and we can get these two quantities. We then optimize this function over these decision variables. And this is the main result. We don't even need to go over those bullet points. The punchline of this is that for this single server model, if I fix the arrival rate and I know the arrival rate, I never use both of the mechanisms at the same time. So for high arrival rates, I just never turn the server off. And then as I progress through, I go through these things. So you can, and it should make some intuitive sense that the lower the arrival rate is, the more important it's going to be to turn off the server, because the lower the arrival rate, the more it's idle. And then the higher the arrival rate, you don't want to turn the server off. That should be intuitive, but maybe what's not so intuitive is that there's this sharp transition between using these mechanisms. Okay, so this is where we are so far with this. So I'll just end with, I'll have these two bullet points and then another comment. So from the analytic modeling side, so in these more mathematical models, the challenge is to, of course, scale this up. The challenge is to move to systems with multiple servers and more realistic demands to the system, time varying, more complicated workflows. We're looking at this. Will these results carry over to practice? So trying simulation or small test beds. We have a small experimental data center at McMaster that we can kind of try these things out on. But I just want to go back to this and end with what we're actually trying to support in the end is the following intuition, or at least provide this analytic support for the following intuition for how I should control these systems. And what we see from here is that if I have a system with multiple servers, what this result suggests is that I have a bunch of servers. What I should do is turn servers on and off on longer time scales. So basically, I want to every now and again right-size my system. I want to have the right number of servers in order to get the load on each of the servers sufficiently high. And then once I do that right-sizing, then I should just use dynamic frequency scaling to compensate for kind of short-term variations and things. So if I'm designing a control policy, I basically want to split it into two time scales. One determines the number of servers, and then the other determines when I should switch between frequencies. And I'll stop there.
So, any questions for Doug? So maybe you can ask and we can repeat the question.
Yes, the first one. What kind of workflow are you running? So we have been thinking of the option of turning the on and off the item, but I mean, it doesn't work in our case. The receive job continuously time to turn on the server. Just, yeah,
So this is an entirely simplistic abstract model. So the
Yeah,
workload.
sorry for interruption. If you could kindly repeat the question for the online
So
audience.
yeah, sorry. So the question was, what kind of workloads are we running here? And the answer is, in some sense, we're not. This is our workload. So I basically just have this abstract model that says arrivals are coming according to this this Poisson process, and then the processing times just follow some distribution. So the question is well taken. This is, I think, getting us some initial insight, but this question of how does this carry over to practice? I think there's some questions, but if one of the things that happens here too is that if the time to turn on a server is sufficiently long, that determines the ranges of when you want to do things. And if the time to turn on a server is sufficiently long, you can essentially get that you never want to turn it off because it just kills everything.
there is always something, and with the manual information. So I don't think it's automated would never work.
But I think that, so one of the things that this says that I think maybe has some potential is it says that it leads the way to saying when you turn servers on and off should be done on a fairly long time scale, and I think that gives you the opportunity to maybe deal with these things. But yes, when I've talked to people, the big objection to turning servers off isn't necessarily these response times. One of the big, the questions when I've talked to these data center operators are, well, if I turn the server off, it might never come back on when I try to turn it on. And that is actually a bigger objection than the time that it takes to come on. And yeah, so sorry, it's a very abstract model.